Greetings, everyone. My name is Anirudh Kandwal, and I am here with my fellow researcher, Bhaskar Pandey, under the guidance of Dr. Sachin Gaur. Today, I'm excited to present our research on detection of diabetic retinopathy and classification of its stages using convolutional neural network. As we all know, diabetes is a rapidly growing global health issue, and the consequences of uncontrolled diabetes can be severe, one of which is diabetic retinopathy, DR. Early detection is crucial to managing the diabetes, preventing complications like blindness. Diabetes detection is crucial for preventing complications like diabetic retinopathy, which can lead to blindness. In this research, we employed a deep learning approach using the DenseNet 169 architecture to classify retinal images into five stages of diabetic retinopathy. The model was trained on APTOS 2019 dataset, which contains around 13,000 retinal images, achieving an accuracy of 82%, outperforming some advanced models. Detecting diabetic retinopathy DR is a challenging task and requires precise identification of various retinal abnormalities. Traditional methods have often relied on manual engineered features and rule-based systems. These systems, though valuable in earlier research, have significant limitations. They depend heavily on expert ophthalmologists to analyze retinal images, and they struggle to generalize well when dealing with large datasets or subtle, complex patterns in images. To explain this, consider how traditional system works. Typically, domain experts would define features such as microanions, exudates, or hemorrhages, which are signs of diabetic retinopathy. Based on these features, rules are created, such as detecting pixel intensity changes or shapes that may indicate abnormalities. However, these handcrafted features cannot fully capture the diversity of retinal structures. Furthermore, there is considerable variations in the appearance of diabetic retinopathy across different patients and even within different images of same patient. This makes it difficult for rule-based systems to accurately detect the early stage of diabetes or differentiate between stages of severity. In addition, these methods are inherently subjective. Their accuracy relies on the skill of experience of the expert, introducing a level of variability. As a result, scaling such systems to analyze large datasets is impractical and prone to error. To address these challenges, we turn to deep learning, specifically convolutional neural networks (CNNs), which offer a robust data-driven approach. Unlike traditional methods, CNNs do not require manually engineered features. Instead, they learn hierarchical representation directly from the data. This means the model automatically identifies key features relevant to detecting DR without needing explicit instructions from experts. Essentially, it shifts the paradigm from manually crafting rules to letting the model learn patterns from the data itself. We employed the DenseNet 169 architecture, a powerful and efficient CNN that has shown great promise in various image classification tasks. DenseNet 169. You might ask, well, DenseNet 169 or densely collected convolutional neural networks has a unique architecture that enhances both learning efficiency and model performance. Let me explain DenseNet's key strengths. Traditional CNN architectures pass the output of one layer to next in sequence, which can lead to challenges like the vanishing gradient problem, where the early layers of the network receive very weak learning signals. DenseNet addresses this by creating dense connection between layers. Here's the clever part. Instead of each layer only passing its output to next, DenseNet ensures that every layer receives input from all previous layers. This improves the flow of information and gradients across the network, leading to more stable and efficient learning. Why does this matter of our task? Well, detecting DR is not just about identifying obvious signs like large hemorrhages. We also need to detect subtle changes in the retina, which requires understanding both low-level features such as edge and textures and high-level features such as more abstract patterns. DenseNet's structure promotes feature reuse, meaning the model can combine information from multiple layers to capture a rich set of features. This is crucial for accurate detecting the various stages of DR, from early signs to more advanced stages. Let's now discuss the data pre-processing phase, which is essential to ensure that the model receives clean and consistent input. Retinal images can come in various resolutions, sizes, and even color variation. To prepare the images for our DenseNet model, we undertook several key pre-processing steps. Resizing the images. We resized all retinal images to 224 cross 224 pixels, which is the input size required by the DenseNet 169 model. This resizing ensures uniformly across the dataset, which is critical for our model to learn effectively. Normalization. This is a technique where we adjust the pixel values of each image to a common scale. Specifically, we standardize the pixel values by normalizing them between 0 and 1. This allows the model to converge more quickly during training, as it prevents large variation in pixel values from overwhelming the learning process. Data augmentation. To improve the model's generalization ability, we apply data augmentation techniques. These includes randomly flipping the images, rotating them, and occasionally zooming in on certain areas. Augmentation helps the model learn to recognize diabetic retinopathy patterns under different orientations and scales, making it more robust to variation in real-world images. It also artificially increases the size of our training dataset, further reducing the risk of overfitting. Now, one of the most critical aspects of our approach was leveraging transfer learning. Instead of training DenseNet 169 from scratch, we utilized a pre-trained version of DenseNet 169, which had already been trained on the ImageNet dataset. ImageNet is a massive dataset that contains millions of labeled images across a wide range of categories. and the features learned from the dataset provide a solid foundation for further learning. By fine-tuning this pre-trained model on our diabetic retinopathy dataset, we significantly reduced the time required for training while also benefiting from the extensive features that the model had already learned from ImageNet. Transfer learning is practical. Transfer learning is particularly advantageous when working with medical datasets, which are often smaller compared to general image datasets. In our case, transfer learning allowed Dansnet 169 to leverage its prior knowledge to focus on retinal features such as detecting abnormalities like lesions or hemorrhages. The model was trained for 50 epochs using the ADAM optimizer. ADAM is widely used because of its efficiency and ability to adapt learning rates from each parameter. We also use the categorical cross-entropy loss function, which is ideal for multi-class classification problems like ours, where the goal is to classify retinal images into different stages of diabetic retinopathy. To avoid overfitting, we incorporated early stopping. This technique monitors the model's performance on a validation set during training. If the model's performance on the validation set starts to degrade, training is halted early, preventing the model from becoming too specialized to the training data. This helps ensure the model generalizes well to nuancing images. In our research, we specifically chose the DenseNet 169 architecture for its unique ability to capture complex patterns through dense connections between layers. Let me explain why this architecture stands out compared to traditional convolutional neural networks CNNs. Typically, in standard CNNs, each layer takes input from previous layer and pass it forward. However, DenseNet operates differently. Instead of relying on the immediate previous layer, it allows each layer to directly access feature maps from all preceding layers. This, this dense connectivity ensures a more efficient flow of information, leading to several advantages. Fewer parameters. DenseNet achieves this connectivity with fewer parameters than traditional CNNs, which makes the model more efficient in terms of memory usage. It also mitigates issues such as vanishing gradient, where signals weaken as they pass through deep layers. By accessing information from earlier layers, the network ensures strong gradient flow, improving learning stability. Reduced overfitting. The dense connections enhance feature reuse across layer, reducing the need for extensive parameters and helping prevent overfitting, especially when dealing with relatively smaller data sets like medical imaging. As we can see from the architectural design, densely connected layers are followed by softmax output layer for classification. The softmax function is ideal in our case because it is used for multi-class classification, helping the network predict the probability distribution over the 5 classes of diabetic retinopathy severity. Each output node is softmax layer represent a probability for one of these classes, allowing us to make a final classification. We didn't use DenseNet 169 as is. We customized the architecture to better suit the task of diabetic retinopathy detection. Specifically, we added additional layers for classification. These additional layers help define the feature map extracted by DenseNet, making the model more tailored to identifying different stages of diabetic retinopathy. In terms of optimization, we opted for the ADAM optimizer, which is known for its adaptability. ADAM adjusting ADAM adjusts the learning rate for each parameter during training, ensuring efficient convergence. After experimentation, we settled on a learning rate of 0.01, which struck the right balance between fast convergence and stable learning. Choosing the right optimizer and learning rate is critical in ensuring the model doesn't get stuck in local minima or diverge during training. Adam's ability to adjust the learning rate dynamically allowed us to avoid these common pitfalls. The model trained for a total of 50 epochs, but we employed a technique called early stopping. Early stopping monitors the model's performance on the validation set, and if the performance stops improving or starts degrading, the training it halted before completing all the epochs. This helps to prevent overfitting, where the model becomes too specialized to the training data and performs poorly on new data or unseen data. Key takeaway here is that the model strikes a solid balance between fitting the training data and performing well on validation set. If the training accuracy had been significantly higher than the validation accuracy, it would have indicated overfitting, where the model memorizes the training data but struggles with new examples. However, our model shows a relatively small gap between training and validation accuracies, suggesting that the architecture and training processes have led to good generalization. However, despite these strong results, there were a few challenges that we encountered, specifically with the misclassification between certain classes. One of the most significant issues was distinguishing between severe diabetic retinopathy and moderate diabetic retinopathy. This misclassification can likely be attributed to subtle difference in retinal features between these two stages of disease. Here we see the confusion matrix for the model's predictions. The diagonal elements represent the correct classification, while off-diagonal elements represent misclassifications. The model performed well in identifying no DR and moderate DR, but struggled slightly with mild DR and severe DR. The confusion matrix illustrates how the model correctly classified most of the no DR cases with 587 correct predictions. However, there were misclassifications, particularly between severe and moderate DR, where 28 instances were incorrectly predicted as moderate DR. This table shows the precision, recall, F1 scores, and support for each class. As you can see, class 0, no DR has high precision and recall, indicating accurate predictions. However, class 1 mild DR had lower precision and recall, highlighting the challenge of detecting mild cases. Now let's discuss the performance comparison of a model with other existing algorithms. We benchmarked our 169 model against well-established methods, including CNN, XGBoost, and deep neural networks, to evaluate its relative performance in detecting diabetic retinopathy. As seen in the accompanying graph, DenseNet 169 consistently outperformed these traditional models in both multi-class and binary class tasks. Specifically for multi-class classification, our DenseNet 169 model achieved an impressive 82% accuracy, which is notably higher compared to alternative approaches, which are only binary classified. This accuracy demonstrated the model's ability to effectively differentiate between the various stages of DR, from no DR to proliferative DR, which is critical for determining the appropriate level of medical interventions. When we move to binary classification, where the task is to distinguish between DR and no DR, our model reached an exceptional 98% accuracy. This performance significantly surpasses traditional binary classifiers that have been used in previous research studies. The high binary accuracy indicates that a model is highly reliable when it comes to determining whether a patient is at risk of DR, a key factor in large-scale screening programs. However, it is important to highlight that multi-class classification holds particular importance in context of DR detection. While many earlier studies focused primarily on binary classification, our approach goes a step further by providing detailed information on the specific stage of DR that the patient is in. In summary, our results not only show the superior performance of DenseNet 169 in both binary and multi-class classification, but also demonstrate that added value of model that can distinguish between all five stages of DR, something that the most existing model falls short on. This comprehensive classification is what sets our approach apart and makes it valuable tool for medical community. Our study shows that DenseNet 169 effectively captures complex features from retinal images, improving diagnostic accuracy for diabetic retinopathy. The multi-class classification approach provides better insights into different stages of DR, which is critical for accurate treatment. In conclusion, we proposed a CNN-based approach using DenseNet 169 for diabetic retinopathy detection and classification. With over 13,000 retinal images, our model achieved 82% accuracy, outperforming existing methodologies. Our research demonstrates that deep learning models like DenseNet 169 can significantly enhance the accuracy and efficiency of detecting diabetic retinopathy. This has practical implications for improving early detection, especially in resource-constrained environments where access to medical professionals may be limited. Future work involves extending this research by incorporating semi-labeled or unlabeled data to improve the model's robustness and scalability. Further, collaborating with healthcare professionals will ensure practical implementation in clinical settings. At the end, we would like to acknowledge the APTOS dataset, the Kaggle platform, and all contributors for providing the dataset that made this research possible. A special thanks to my fellow researcher Bhaskar Pandey and our guide Dr. Sachin Gaur for their invaluable support throughout the system. Thank you. The 9 DenseNet 1 detection diabetes is a